Okay, welcome to the next video in this standard quiz model series, going through the solutions to the standard quiz model. I'm talking about the questions that are on the 2019 AP Calculus AB Term 1 standard quiz. So in this case, we're going to look at a question that's brand new to the standard quiz, but one that I think is actually a really helpful one, especially towards taking the AP exam when that eventually happens, as well as the actual unit assessments during the course, which is one that's basically just a true or false question every single time dealing with conceptual parts of calculus. So this just kind of gives you exposure to a little bit of the different sorts of questions that we might ask and some of the ways you might think your way through here. Kind of guide your thinking as you go attack these guys. So we're going to start with 11a. And 11a states that if f of 3 is negative 2 and f of 5 is 6, then f of c has to equal 0 for some c in 3 to 5, in the open interval 3 to 5, by the intermediate value theorem. So at first glance, this question sounds like this statement sounds like it's probably true. Basically, we're going from a negative y value to a positive y value, and then you'd think for sure that there must be a 0 value inside. But actually, this question is false, or this statement is false. The reason that this statement is false is not a part of the standard quiz. You don't have to state why it's there. But if you want to think about exactly why, let's imagine our scenario. So we have some function f of x, where f of 3 is negative 2. So there is there is negative 2, and there is 3. And then it says f of 5 is 6. So if we go over to 5, go up to 6, there's 6, and there's 5. So in a sense, you want to say, well, look, it's got to go all the way up there. But the truth is we don't know that that's exactly what happens. We could have a situation where instead there's some sort of discontinuity somewhere in the middle, meaning that we never actually hit that. So our reasoning here would be that the IVT requires continuity. So without continuity being guaranteed, we can't use the intermediate value theorem to make any sort of statement or assumptions about what values of y are attained in between x equals 3 and x equals 5. So there's one of those kinds of things. In this case, I'd say this true or false statement is a missing information one. They give you a very apparently true statement, but there's something missing about the requirements, particularly when you see a theorem like the intermediate value theorem invoked. If you don't see all the pieces required for it, then that probably tells you it should be false. You could create a situation like we just did where that was untrue. For part B, 11b, it says if the limit as x goes to 5 of g of x is infinity, then the limit as x goes to 5 of 10 over g of x must be equal to 0. So a couple things here. Like, I do know the answer to this one, but really quickly, to illustrate our thinking, basically what we can do is we can use the quotient property. We can say that this is equivalent to the limit as x goes to 5 of 10 over the limit as x goes to 5 of g of x. So evaluating these things, 10 is a constant function. Everywhere its value is 10, so the limit is definitely equal to 10. And down below, we were told that this was equal to infinity. And although this isn't equal in the traditional sense, 10 over infinity does in fact go towards 0. So the limit as x goes to 5 for this function should in fact be 0, making this statement very much true. So I'd say this is probably one of the simpler ones. It's testing your ability to know some of those properties of infinite limits. Really important property at that, though. Okay, the third one says, for part C, it says the function r of x, which is given by that rational function, has a vertical asymptote at x equals 3. So my thought here is if we want to talk about vertical asymptotes, we need to make sure that our limit goes to infinity and not to some finite value. So we've got to be able to distinguish between when a vertical asymptote occurs and when possibly a point discontinuity or a removable discontinuity like a hole would actually be there. So my thought process is that I'm going to go ahead and factor r of x and try to see if anything simplifies. Maybe that would help us. Because as of right now, vertical asymptote at 3, I see that 30 minus 30 in the denominator does equal 0. It seems like it might be a candidate, but let's find out. So in factoring this guy, I'm going to first factor out my denominator. I'm going to factor out a negative 10, and it'll leave me with negative 10 times the quantity x minus 3. So it doesn't really help us a whole lot, but at least we can see that there is a potential for a vertical asymptote down there. The numerator, though, let's say we want to multiply to negative 24 and add up to 5. I'm thinking that's going to be x plus 8 and x minus 3. So this is actually super important information. What we've just shown is that x minus 3 is a factor in the numerator as well as the denominator. So in fact, those two things divide out, meaning that r of x is actually equivalent to a function x plus 8 over negative 10 for all x values except for 3. What that means that division away is that we've removed that 0 over 0 hole that was there. It means that there is in fact a hole at x equals 3. Now if there's a hole at x equals 3, there can't be a vertical asymptote. So not a vertical asymptote. And what that means is that this statement is in fact false, because there's actually a removable discontinuity there, not a vertical asymptote. So in this case, it was knowing what the difference was between a vertical asymptote and a hole. Really important piece of information and task to know conceptually. Okay, for part D, it tells us that the limit as x goes to 7 from the left side of h is equal to the limit as x goes to 7 from the right of h. It says if those two one-sided limits are equivalent, then h of x is continuous at x equals 7. So this one's involving continuity. So now thinking about our implications here, we have a left-hand limit equal to a right-hand limit. Now the implications of left-hand limit and right-hand limit being equivalent means that the limit at that x value, in this case the limit as x goes to 7 of h of x, will in fact exist and be equal to the same as those other two. So that's nice to know. But it doesn't ask us, does the limit exist here? It asks us, is the function continuous at x equals 7? So now here's the problem. So if we think about the definition of continuity, there are 3 requirements. The second one is, of course, what we just saw, that the limit as x goes to 7 of h of x must exist. But the first and third both involve the actual function value. We'd need to show that h of 7 is defined, and then finally, that h of 7 is equal to the limit itself as x goes to 7 of h of x. Now, given information about the left-hand and right-hand limits, we can only guarantee information about the limit itself. Our situation could easily look like this, where our limit clearly exists, but then there's either a missing point or a removed point from the actual function or the graph. So in fact, what that means is that we don't have enough to guarantee anything about the function value itself, so that makes statement 11D also false. So there we go. So I think our statements went false, true, false, false so far. Keep that in mind. Okay, that brings us to the plus question. And the plus question, again, could go in a lot of different directions, but again, the answer is just true or false, so I guess you always have a 50-50 shot. But let's see if we can work our way through it. So in the P question, it says the graph of function f given by that piecewise function has exactly 2 discontinuities. So basically what we're going to need to show is either that there are, or what we're going to want to show if we want to confirm that we can get this correct, is we want to either show that there are 2 discontinuities, not any others, or that there's either less or more. So lots of different pieces for us to look at here. Where I'm going to begin, though, is I'm going to focus my attention for when x is less than or equal to 1. That's going to be my starting spot, because I see a fairly interesting function. So for x less than or equal to 1, f of x is going to be equal to 10 over x times x plus 4. Oh, excuse me, it's not even 10 over x. It's 10x over x plus 4. So looking up here, this is important for us to notice. I notice that the x's divide away, which tells me that there's going to be a hole at x equals 0. Now, just because those things divide away doesn't mean there actually is a hole. We need to make sure that we're in the correct domain area. We've got the right x values where 0 would be defined. But since x is less than or equal to 1 and 0 is less than or equal to 1, that means that we do in fact have one discontinuity at x equals 0. Now once we're there and that divides away, we're left with 10 over x plus 4. And that would suggest that there's a vertical asymptote at x equals negative 4. Now, and of course the reason being the denominator goes to 0 and the numerator does not. So now negative 4 is also less than or equal to 1, which means that in fact this is also going to be 1. So right now we have exactly 2 discontinuities, and it's very tempting to just go true, good job, and be done. Unfortunately, there's one last thing we need to hit. Although the right branch, when x is greater than 1, is just a constant function, which suggests really smooth, simple continuity, we do have to make sure that there's not a jump at x equals 1, because that boundary might actually have an area where the left-hand limit and the right-hand limits are not equal to one another. So we need to check that as well. So what I'm going to do is I'm going to calculate each of those 2 limits. And again, I would probably do these in my head if I was doing this on the actual standard quiz, but for now we can work our way through. So first I want to look at the limit as x goes to 1 from the left side. That would require us plugging into the 10x x squared plus 4x function. So that's going to be 10 times 1 over 1 plus 4. That's going to be 10 over 5, which is 2. So at this point, getting 2 as our limit doesn't tell us anything. It just tells us that if this function is to have a continuous spot at x equals 1, we need the right-hand limit to also be equal to 2. So let's compute that right-hand limit. The limit as x goes to 1 from the plus side of f of x, so we're going from the right. In this case, that's just going to be 3. So our limit is equal to 3. Now, unfortunately, 2 does not equal 3, which implies that the left-hand limit does not equal the right-hand limit. And that's huge because that tells us that there's actually going to be a jump at x equals 1. A jump is a discontinuity as well, which means that we actually have 1, 2, 3. And even if there were more, we've at least proven that there are at least 3 discontinuities, which means that this statement is definitely false as well. And again, with all these questions, you've seen me do a ton of work as I work my way through them. Keep in mind you don't have to show all that work. This is just a simple statement, true or false. But hopefully you do kind of train yourself to think your way through that, because that's exactly what we do on the AP exam. So there is the video outlining question number 11.